too far into our discussion today, let's pause for a moment and recognize that if you've watched a little bit of the video, you notice that at the end of the jump, there's a little ramp. So I have like 20 minutes of slow-mo footage of the car hitting the end of the ramp and jumping, which I was going to use for a little more of this to talk about how at the end of the ramp you can adjust the angle, and we could take a look at different launch angles and what the result of those different launch angles are. The problem is that real physics and the ideal physics, they are not the same. And oftentimes we're able to kind of overlook some of those problems, but sometimes there's just no way around it. And unfortunately, Hollywood has not done a great job of giving us realistic examples from which to work. Consider this. There's any number of movies that you could have seen that will have, the idea that Josh suggested of me jumping my Jeep or jumping any vehicle. And we have this idea that the car can successfully make a jump from some height. And although it might not land great, it'll probably land and drive away because that's the way movies are. But what's missing here is when movies do this, there's a crane attached to the vehicle. And the crane isn't necessarily to gently lift the car and drop it on the ground. The crane is there because of the reality of physics. You see, the thing that you get to see, and I'll post this as kind of like outtakes so you can see what I'm talking about, is that when the car actually makes it to the edge here, with one wheel on and one wheel off, it might happen fast, but that doesn't change the fact that during this time, there's an unbalanced torque acting on the car, which is going to pull the front end of the car downwards while the back end of the car is still in contact with your ramp. And this torque is going to occur whether we're driving off of level surface or we're driving off of a ramped surface, which is going to begin an angular velocity of the car, which means the car doesn't just simply roll off the edge and land flat. The car tumbles off the edge and spins until it hits the ground. That might be one rotation and it lands perfectly on its wheels, but more than likely, it's not going to be like that. The car is going to have something spectacular happen on its way to the ground. So I want to be very clear that what we tend to see in the movies has kind of given us a false sense of what's really happening. And that's going to be especially true with today's example. Now, the problem with today's example, and when I say problem, I mean problem that I have with not being at school with all of you, is there's a significant disconnect, something that's much more difficult for me to do. Because I could ask of you a question and walk the room real fast and see if you're making a quick run of it or not. And I don't get that option here. So in lieu of that, I'm going to see at what level the room is at currently. If you paid attention to the video, you know that the top of the loop was 20 centimeters above the ground. Theoretically, what would have to be the minimum height to successfully navigate the loop? We talked about it yesterday. So I'm going to give you a few minutes. I'm looking for a value in centimeters, and I'm willing to let you talk it out with people so that you can kind of get a sense of it, maybe try not to make a mistake. So I'm going to send you guys into some rooms so you guys can talk these out a little bit, but I'm only going to give you like 3-4 minutes. When you come back, I'm expecting you guys to put your minimum height in the chat window. Okay, everybody have the dynamics of the question? All right. Why don't you go to your room real quick, find somebody to work with, or I'll give you somebody to work with, and I'll see you all in just a minute. But that puts us in a precarious position, and here's why. We're looking to see if you guys can functionally work a problem where you're attempting to figure out what the minimum height is in order for the car to reach this point and have enough velocity to make it through the loop. So let's assume that you guys did the work as expected. Does it change your answer if the loop had a radius of 30 centimeters? Are you reworking the problem? And what I want you to pay attention to is something I said yesterday about this whole thing. We know that the reason the car makes it through the loop at all is because it has enough energy to make it to the top of the loop, plus enough kinetic energy so that it can stay in uniform circular motion. Both conditions have to be met. So this is condition number 1. And condition number 2, hopefully you all saw this, is going to be mgh min is going to be equal to 1/2 mv squared plus mg times 2r. We're assuming that the loop starts at the ground. Does that make sense to everybody? Or any question about that? So these are the 2 conditions that we expect have to be met for the vehicle to successfully make it through the loop. Now, the right condition is pretty fleshed out. There's not a whole lot that we have to add to that. But the left condition, we probably should look at a couple of things that affect it. We know the car is experiencing 2 forces here, mg and normal. We know velocities that are too fast just to increase how much normal force there is. It's when our velocity gets smaller where we start reaching our limits, and that particular limit is when the normal force goes to 0. So that gives us normal plus mg equals mv squared over r. A lot of shared variables between these two, but again, the conditional is knowing that our normal force is going to 0. Now, you could have quite easily figured out what the minimum speed is by simply using the information that was presented. You know, the mass cancels out. So successfully, assuming you used 10 for g, you were probably able to figure out what that minimum speed was because I gave you the radius of 0.1. But I would like you, again, to consider perhaps looking at the problem from a slightly different perspective. Look, I have a shared set of variables here, mv squared, mv squared. Let's use that to maybe make a broader prediction. For example, on the left side, I'm going to write this as mgr equals mv squared. I've just multiplied both sides by r. Any problem with that? All right. So I'm going to go one step further because I want it to look like 1/2 mv squared. I will multiply both sides by 1/2. Now, here's the rub. I mean, what I've really done here is I found a different way to express the kinetic energy based on the condition to stay in uniform circular motion. So I'm going to make this substitution. Now, I know some of you have a difficult time following this kind of math, and there's a reason why I want to walk through it this way. No numbers, just using these symbols. I'll get mgh min equals 1/2 mgr plus 2 mgr. Now, all of you are adequate and sometimes above adequate algebra students. You do notice that, right? Do we all see that? All the mg's cancel. And on the left side, I get h min equals 1/2 r plus 2r, which is 2.5 r. Now, the bigger story here is this has to be true for every roller coaster. No matter what size it is, no matter what you want to do with it, if you want to have a 360 loop in your roller coaster, your lift hill will have to be 2.5 times the radius of your loop. If you lift your loop up off the ground, you're going to have to add that distance too. Now, test riders know this, which is why I could have told you this from the beginning. Here, just memorize this. The minimum height for any roller coaster loop problem is going to be 2.5 times the radius. You would always then know, if I gave you the radius of the loop, you would know how high the first lift hill has to be. So I tell you it's a 20-meter loop. You immediately know, all right, 2.5 times 20 meters, that's how high the cars have to be in order to successfully make it through the track. But that's not true. That's not the way they're going to have to frame it. They don't want you to have something that you can memorize. More importantly, if you watch the video, you know that I had to lift a car higher than the 25 centimeter mark to successfully make the cars go through the loop. In fact, I had to get closer, like 30 centimeters, for the cars to successfully make it through the loop. Now, if you're thinking that the reason has to do with the typical trope of stuff that we would say, air resistance, friction, and all that kind of garbage, you understand that, yeah, if I was an AP test rider, I would definitely want you to be able to state why air resistance would make it so you would have to start the cars higher. And I would expect you to indicate that there's some energy taken away from the system due to air resistance, or energy taken away from the system due to friction. I would expect you to be able to write that out and expect you to figure out how it affects how we deal with conservation of energy in a paragraph form, all that kind of stuff. But the real issue is that's not how it works. If you look at Scorpion's lift hill is not 2.5 times the height of the first loop. It's lower than 2.5 times the radius, which goes against the whole idea that we should have to start the car higher. Why is it that when you ride the Scorpion ride, it doesn't have to lift the cars too much higher than, it doesn't have to lift them 2.5 times the radius. And there's great pictures of Scorpion. Look at all of them. You can almost measure it on your screen. The fact that the lift hill is not 2.5 times the radius of the loop. Yet it's a perfect 360-degree loop. And here's the point of today's discussion. I suspect that about 75% of you could do this, could be trained to do this, could figure out the minimum height of a roller coaster. I say that because that's been about my expectation in class. Through repetition or understanding, 6th period has a pretty high turnout for problems that involve something like this. We know the AP exam isn't going to be like this. Yeah, they want you to know this, they want you to be able to do this, but they want to be able to throw you a curve and expect you to deal with it. They want to talk about how is the real world similar to the theoretical world, and how is it different? To give you an idea of what I'm expecting is, let's take a look at this from the standpoint of a real roller coaster and how it might be different than what we're anticipating. You see, this theoretical garbage assumes that our roller coaster cars, A, defy physics because they experience no friction and no air resistance, that they are perfect point masses, and that the track can give infinite amounts of normal force when necessary. But that's not the case at all. What I mean is our roller coaster is a train of cars. Right? 8, 10, 12 ride vehicles all connected together. I want you to think about this for a moment. Every single one of these cars has to make it to the highest point in the ride. Every one of them. But does the center of mass of the system ever make it to the highest point in the ride? If you don't understand what I'm asking, imagine maybe the midpoint of the loop. The moment that the middle car is here, there's half of the cars on this side and half of the cars on this side. And if you've ever ridden the Scorpion, you know what I'm talking about. At this instant, is the center of mass of our trains at the highest part of the loop? And the answer is no. The center right now is somewhere around there, with about half the weights of the cars above that line and half the weight of the cars below that line, suggesting that the center of mass of the cars might never make it to the highest point, which means the cars might never have to have that amount of energy. On the other hand, we don't really know how much energy the system has anyways. Because when the cars go over the top of the first hill, they are never all at the top at the same time. Not in Scorpion. Now, how many of you have ridden Sheikra? All right, now Sheikra isn't like this at all, is it? Sheikra is a very short car, but it's very wide. But also, when you ride Sheikra, do you realize that all of the cars are at the very top at the same time? Similarly to Montu, Montu's cars make a 180-degree turn after they make it to the very top of the lift hill before they go down the first ramp, ensuring that the entire center of mass of the system is at that height. But Kumba doesn't do that. Kumba turns and dives almost immediately. And definitely Scorpion does that as well. You make it to the top of the first hill, you turn and dive almost immediately. Which means it's really hard to gauge where the amount of energy actually is. You might think we would deal with the center of the cars, but when? When do the cars have their maximum amount of energy? Believe it or not, on Scorpion, they can't have their maximum amount of energy until the last car is off of the chain lift. Which means in Scorpion, that's when all of the cars have already begun their descent. So the real world definitely has more complications. And as you can see, these are definite problems that AP Central could throw at us. Our job is to understand the ideal case first. Let's understand the ideal. Then we should be able to apply the ideal case to these kinds of cases, being able to perhaps explain what is happening. Real roller coasters are more complicated. By the way, why does the track shake as the cars go through it? Anybody have a theory? Let me consider the ideal case for just a minute. And I want to consider when the car is right there with a velocity in this direction. What would be the direction of the normal force right now? It's hard for you to point because some of your cameras have reversed your image. So the direction you might be pointing might not mean anything to me. So, left or right? So the track pushes on the cars in this direction. It has to be perpendicular to the track, and it has to be in such a way as to cause circular motion. So left is the right answer here. Now listen carefully. The track pushes on the cars to the left, which means by Newton's third law, the car pushes on the track to the right. There's a force on the track from the car. And if the track isn't perfectly rigid, and let me tell you, plastic Hot Wheel car tracks are not perfectly rigid, the system shakes. But so too do all roller coasters. Look, all roller coaster tracks shake when the cars go through them. They all have to shake. They have to respond to that force. They're not going to be perfectly rigid. And let me tell you, how many of you watch your friends ride roller coasters because you don't want to? There's got to be a few of you here, and I'm sure that you're out there. Look, if you sit and watch The best one to watch for this is Kumba. Kumba's really tall and really old. There's a lot of metal fatigue. And because there's metal fatigue, you'll see the whole thing swaying as the cars go through it. Some of them get really bad. In the old days, the Python was the worst because it would shake vigorously about 6 feet in either direction on the first hill. So some of these can be really intense. Montu shakes quite a bit, but its track is so distributed, it's harder to see because you're not out there amongst the track as much as you are with Kumba. So this shaking of the tracks is a response to Newton's third law. And there's really no way around it. Those track pieces are going to experience a force, and therefore they're going to be accelerated in one direction or another. All right.